All right, so today's lesson we're going to talk about independent events and dependent events. The difference between independent events and dependent events is that independent events are just what they're sound. They're independent of one another. They don't rely on anyone else. When you are independent, you don't rely on someone to help you with your homework. You don't rely on someone to pay your bills. You're independent. You do it on your own. When you're dependent of someone, that means anything you do is dependent of what they do or what someone else does. Okay, so an independent event would be like you have a dice and a spinner. If I roll the dice, that's not going to affect what I land on my spinner. A dependent event is going to be an event that depends on what happens the first time. So if I have a bag of marbles and I take one out, that changes how many marbles I have left in my bag. So it depends on what color I ended up pulling out because that's going to change my probability for the next event. So independent is something that does not affect the other. So if you look in your book, I'm going to go through example 1 and 2 and probably another. Okay, so in your book, the first example is talking about selecting letter tiles and a spinner. Again, it's independent because whatever letter tile doesn't affect my spinner. I can pick a G and I can still spin anything. I could pick an A and still spin anything. It doesn't matter. It's independent. So there's two different ways we could do this. I'm going to do this the tree diagram first, and then I'm going to do it the algebraic way. So the first time we would have a tree diagram is we look at the options that we have for tiles. So I have an option of G, B, E, and A. If I pick a G, what are my options on my spinner? Well, I have A, B, and C. If I selected a B tile, I still have the options of A, B, and C. Same thing here, A, B, and C. A, B, and C. So those are my total outcomes. And you can see that I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total outcomes. And remember, your total always goes on bottom. It's favorable over total. But now, what is our favorable? So we were asked to find the probability that both will be a vowel. Well, if you remember, our vowels are A, E, I, O, and U. So if we go here, A is a vowel, but G is not. So that's not both being vowels, so that does not work. That's not both vowels. That's not both vowels. A is a vowel, but B is not, so this does not work. That does not work. That does not work. A is a vowel, and E is the vowel, so that one works. B is not a vowel, C is not a vowel. A is a vowel, and A is a vowel, so that one works. But B is not a vowel, and C is not a vowel. So I have two options out of my 12 total options where they're both vowels. Then we can reduce this to 1/6. And if we typed in 1 divided by 6 into our calculator, we would see that it's 0.17 when rounded to the nearest hundredth, and that would be 17%. So this would be our final answer. Okay, I said I was going to do it the algebraic way. So if you don't want to write out your tree diagram, and some situations you're not going to want to because they're going to be so large, we can do it a different way. We're going to take the probability of the first event, and we're going to multiply it times the probability of the second event. So what that looks like is, again, if I look at my tiles, how many options do you have in your tiles that are vowels? Well, I have E and A. So I have 2 out of 1, 2, 3, 4 tiles. Okay, that's my first event. Then I'm going to multiply it times my second event. So if I look at my spinner, what options do you have there that are your vowels? Well, you have A, which is 1 out of 1, 2, 3. 2 times 1 is 1. 4 times 3 is 12. Oh, sorry. 2 times 1 is 2. 4 times 3 is 12. And that reduces to 1/6, my decimal, and my percent. So we got the same answer, we just did it a different way. If you like to draw tree diagrams, you can do it that way. I would know that you're going to multiply because some of these situations that I talked about, we're not going to want to draw out tree diagrams. So let's go to example 2 in our book. So in example 2, this time we have a dice and a spinner. So it says the spinner and number cube shown are used in a game. The probability of not spinning a blue and then rolling a 3 or a 4. So again, you could draw a tree diagram. So my options are 1, 2, 3, 4, 5, and 6 on my dice. And then for each of those numbers, I have the option of rolling a purple, blue, yellow, green, red. So purple, blue, yellow, green, red. And I could write those all out for 2, 3, 4, 5, and 6. But you can see that I am going to have 1, 2, 3, 4, 5 in each. Okay, so I have 5 options for when I roll a 1. I have 5 options when I roll a 2. I have 5 options when I roll a 3, 5 options here, 5 options here, and 5 options here. So if I took 5 times 6, I could see that my total outcome, or possible outcomes, would be 30. But I need to know what's the probability of not spinning blue and then rolling a 3 or a 4. Well, what's not spinning blue? Purple's not spinning blue. Yellow's not spinning blue. Green's not spinning blue. And red's not spinning blue. Okay? So for each of those colors that I spin, I need to also roll a 3 and a 4. So if I spin a purple, I need to roll a 3 and a 4. If I spin red, I need to roll a 3 or a 4. If I spin green, I need to roll a 3 or a 4. And if I spin yellow, I need to roll a 3 or a 4. So you can see that our favorable outcomes, there are 1, 2, 3, 4, 5, 6, 7, 8 out of our 30 total outcomes. We could then reduce that to 4/10, and again, you could reduce that to 2/5. Okay, we would type in 2 divided by 5, and you would get the decimal of 0.4 or 40%. Okay, so I kind of did that tree diagram a little bit different than what I've been doing the other ones, just because I didn't want to draw out a total of 30 options. That's why I think this would be a situation where using our algebra way would be a little more helpful. So the algebra way, we want to know the probability of not spinning blue. So if I look at my spinner, I have 1, 2, 3, 4 options out of 1, 2, 3, 4, 5 that are not blue, times my probability of rolling a 3 or a 4. Well, I have 2 options on a dice that are either 3 or 4. And I have 6 total options. 4 times 2 is 8. 5 times 6 is 30. And again, you would reduce this. You get 2/5. and then you would write that as a decimal of 0.4 or 40%. So those are independent events. The dice did not affect the spinner. All right, this problem is not in your book, so if you want to write it down as I go, you can. It says a red number cube and a white number cube are rolled. Basically, a red dice and a yellow or a white dice are rolled. The faces are numbered 1 through 6. What is the probability of not rolling 3 on the red number cube and rolling the number 3 or less on the white number cube? Okay. I don't want to write out all the options because there's 36 options. So I'm going to use the algebraic way to solve this. So if you think about it, on your red dice that's numbered red 1 through 6, how many options do you have that are not 3? Well, you have 1, 2, 4, 5, 6. So you have 1, 2, 3, 4, 5. 5 out of my total options on the dice, which are 1 through 6, so 6. And then I'm going to multiply that times rolling the number 3 or less on the white number cube. So 1, 2, 3, 4, 5, 6. Those are my total options, so there's 6 of them. And the numbers that are 3 or less. So we're going to include 3 this time. So we have, you can see 3. 5 times 3 is 15. 6 times 6 is 36. We can divide the top and the bottom by 3, which gives me 5/6. And then you can type that into your calculator, 5 divided by 6, and you get the decimal 0.83, which is 83%. So this is the video that covers independent events. That first dice didn't affect the second. The next video is going to be a video on dependent events.